Bismillahirrahmanirrahim. Electrical network analysis, and we are using the introductory circuit analysis book by Robert L. Boylested. And today our topic is the resonance. So, chapter number 20 is the resonance chapter by this book. Okay, so what is resonance? Knowing the fundamentals of a resonant or the tuned circuit is very important to the operation of a wide variety of electrical and electronic circuit in use today. So, the most important example for the resonance is the radio. So, this is the voltage current graph versus the frequency. So, Mm, at these are all the frequencies values, but at this frequency we are getting the maximum power. So it means the circuit is tuned at this frequency. So this frequency is called the resonant frequency, and we can say that the circuit is at resonant mode. Okay, so the best example is the radio. When we are rolling the frequency and we are searching for the channel. For example, 106.2 is the radio channel. So if we are tuning to the 105, 105.1, 105.2, and at least when we are reaching to the 106.2, so at this point we are getting the maximum power. So then we are listening to the sound. So the at this point the circuit is at resonance. The resonance circuit is the combination of R, L, and C. For any resonance circuit, these three elements are necessary. The response is a maximum for the frequency FR, as I have already discussed. These are also the frequencies values, but at these frequencies, the response is very poor. The response is very poor, but at that frequency, the response is maximum. This frequency is called resonant frequency FR. When the response is at or near the maximum, the circuit is said to be a state of resonance. Although this is not the resonance frequency, but at these points, and we are also getting mm, a reasonable power at this point. At this point, this is the maximum. This is the maximum, but at these values are also good. So these frequencies can be counted for their resonance frequency. For example, if this is 106.2 and this is 106.1 and this is 106.0. So when we are tuning to 106.0, although the maximum power is at 106.2, but still we are listening to the sound of the music or anything. So this frequency can be counted in the resonance frequency, although the quality of the sound will be not as good as here. So but we can count because the power we are getting here is not that much bad. So uh, here they've told that when the response is at or near. So I was explaining this point at the near the maximum point, the circuit is said to be in a state of resonance. The resonant electrical circuit must have both the inductance and capacitance. In addition, resistance will always be present to control the shape. The shape of the circuit can be controlled with the value of the resistance. So there are two types of resonant circuits: series and the parallel. Okay, so now we will discuss the series resonant circuit. Uh, the total impedance of the network at any frequency. This is the series resonant circuit R, L, and C. So total resistance will be equal to R plus JXL minus JXC, or R plus JXL minus JXC. So the point is, when this circuit will be at resonant, or we can say when this circuit will be converted to the resonant circuit, when this XL is equal to XC. When XL is equal to XC, so this we can say that now the circuit is the resonant circuit. So this is, we can say, this is the condition for a resonant circuit. Okay. So as XL and XC are equal, let's suppose this is 10, this is also 10, 10 minus 10, 0. So Z total will be equal to R. As XL is equal to XC, now we are going to find the value for the F. This S means the resonance frequency uh, due to the series resonance circuit. XL is equal to XC, XL is equal to omega L, XC is equal to 1 over omega C. So by taking this omega to here and L to here, so omega square will be equal to 1 over LC, or taking the square root, omega is equal to 1 over LC under the root. As omega is equal to 2 pi f, so f will be equal to 1 over 2 pi. Uh, so omega f is equal to 1 over 2 pi LC under the root. The current through the circuit at resonance, let we have E at an angle of 0 degree, R at an angle of 0 degree. At resonance, Z is equal to R. So we will now discuss uh, XL and XC, because these two are cancel out because of the same value. So I will be equal to E divided by Z, or Z is equal to R. So I is equal to E divided by R. Since the current is same through the capacitor and the inductor, because this is the series circuit, so the current through the inductor will be equal to that through the capacitor. So the voltage across each element will also be equal in magnitude, but 180 degree out of phase, because V is equal to IXL. So I I at an angle of 0 degree, JXL. So J means 90 degree. So IXL at an angle of 90 degree. This is the voltage drop across the inductor. Now voltage drop across the capacitor will be equal to I at an angle of 0 degree, same I, and XC minus JXC, XC at an angle of minus 90 degree, IXC at an angle of minus 90 degree. So IXL, XL and XC are equal. So IXL and IXC will have the same value, but these two are out of phase. So if we draw, uh, I and V are will be in phase with the E, because they have the 0 degree angle, and VL at an angle of plus 90 degree, and VC at an angle of minus 90 degree. So these two will cancel out. This will be cancel out because VL and VC have the same value. So the actual uh, phasor diagram for the series resonance circuit will be these black arrows. Since XL is equal to XC, so magnitude of VL, these XL and XC are same, I are same, so VL and VC are also same. Means voltage drop across the inductor will be equal to voltage drop across the capacitor. Okay. Now the power triangle, uh, as the reactive power QL is equal to I square XL, and QC is the reactive power for the capacitor. So QC is equal to I square XC, as I XL value are same as I XC. So XL and XC will be equal. XL and XC will be equal. So P, if we have no Q, means Q cancel out, because we have the inductor, we have the resistor, we have the inductor circuit in series resonance circuit, we have the capacitor. So Q for reactive power for inductor QL, reactive power for capacitor QC, these two are equal and opposite. So the only power is the P power. So as we have already discussed, P is equal to S is equal to P plus minus J plus J Q minus JXC, as these two are equal. So S is equal to P. So the actual the real power triangle for the series resonance circuit will be these black arrows. Okay, now moving to the next slide. The quality factor. The quality factor of a series resonance circuit is defined as the ratio of the reactive power of either the inductor or the capacitor, because uh, either inductor or the capacitor, because the reactive power Q for the inductor circuit or reactive power for the capacitor circuit, these two are equal, as we've discussed in the previous slide. So if either we take this or this, both are same. So mm, okay, don't confuse this Q with this Q. This Q is the quality factor and this Q is the reactive power. So the definition of the quality factor is the ratio of the reactive power, means reactive power by inductor circuit or the capacitor circuit, to the average power, and this is the power dissipation by the R. So we can denote it by I square R. Okay, so uh, it can be also defined as the ratio of the peak energy storage stored in the resonator to the energy lost. It means because L and C are the energy storage devices, elements. So the energy storage uh, stored in the resonator to the energy lost or energy dissipated, because this is the dissipation. So in other words, the quality factor is also an indication of how much energy is placed in storage compared to that with the dissipation. Means if the storage is greater than the lost, so quality factor will be greater than 1, and if the dissipation is greater than uh, the energy storage, then Q will be less than 1. Okay. Moving to the next slide. Okay, as we have discussed, Q is equal to reactive power I square x xl or I square xe over I square r. I square cancel out, so Q will be equal to xl divided by r, or omega xl is equal to omega l divided by r. This is the another formula for the Q. Okay, as omega is equal to 2 pi f and f is equal to 1 over 2 pi LC under the root for the resonance circuit. So according to this formula, Q is equal to omega L over R, and discuss omega L over R. So replacing the omega value, omega is equal to 2 pi f L over R, and as we know that f is equal to 1 over 2 pi LC under the root, so replacing the f value over here, 2 omega cancel out, so we will get L over R and LC under the root. Okay, now multiplying divide by the uh, L square, so this L under the root, this L under the root, and this L under the root will multiply to get L only L. So this L will then cancel will be this L, so we will left with this L under the root. So Q is equal to 1 over R L under the root over the C under the root. So Q is equal to 1 over R L over C whole square root. So this is another formula for the Q. It depends upon the given values. If we are given with the R, L, and C, so we will use this formula. And if we have the XL or the omega L, then we will use this formula. And if we have the reactive power or the average power, then we will use this formula. Okay. By voltage divider rule, this is the okay. So VL is equal to XL total voltage over Z total. As we know that at resonance, the Z total is equal to R, so VL will be equal to XLE over R. This is the voltage drop, and as we know that VL is equal to VC, so similar will be the case with VC is equal to XC E total over Z total. Z total at resonance is equal to R. So VC is equal to XCE over R. As XC and XL are equal, E and R e- equal, so the VL and the VC will be same value. Okay, XL over R is equal to Q in the previous slide. XL over R is equal to Q. So XL or R is equal to Q. So VL is equal to QE. Similarly, VC is equal to QE. Okay, now we will discuss the curves, as we have already discussed in the class that XL over frequency, this is the linear graph, and XC over frequency, this is the inverse graph. So in series resonance circuit, we have the R, the L, and the C. So for this is the XC graph and this is the XL graph. In this region, we have divided this the graph into two regions. XC is greater than XL and XL is greater than XC. As we have seen, XC in this point, XC is greater at these frequencies. XC is greater than XL. This is the XL values, and at these frequencies the XL value is greater than XC, because at these frequencies the XC is going to 0. So this is the XL greater than XC region, and this is the XC greater than XL region. Okay, now the point where both XL and XC intersects, so this is the point where XL is equal to XC. This is the point. So, and we can say that this is the At this point, the frequency is series resonance frequency. So this region cancel out with this according to the area under the curve, and this region cancel out with this. So we will have the curve only in this region. In this region, this is the graph. Okay, and this is actually the R value. Only upward shift is given to the graph due to this R value. If we have the R value over here, then the graph will be like this, because this is the R value, so the graph will be like this. Okay, okay, now z total is equal to R square plus xl minus xc. This is the imaginary region and this is the real region. So for the magnitude of z total, real square plus imaginary square, xl minus xc, this is the reactive component. So we can write xl minus xc is equal to x. So the real component square plus the imaginary component square, this is the z total magnitude in term of frequency, and this is the graph for z total versus the frequency. Now moving to the angle for the z total. Okay, now theta is equal to imaginary tangent inverse imaginary component over real component. The imaginary component is xl minus xc over the real component is r. So if for this region xl is greater than xc, so at this region the theta will be, if xl is greater than xc, for example xl is 10 ohm and xc is 5 ohm, so 10 minus 5 means the numerator value will be positive. So xl is greater than xc. For the positive value, and this is the region for xl is greater than xc. Okay, so as xl is going to is greater is increases than the xc, the theta the theta will leads to the 90 degree. This is 90 degree, and where if the xl is equal to xc, so at this region the theta is equal to 0, because when xl is equal to xc, xl will cancel out with the xc. Let's suppose xl is 10, xc is 10, 10 minus 10, 0, 0 over r, 0, and tangent inverse 0 is also 0. So this is 0. When xc is greater than xl, if xc is greater than xl, then numerator value will be negative. So tangent inverse of the negative angle is equal to minus tangent inverse, means theta will be negative. So as the xc is greater than xl, the curve is going to decrease and leads to the minus 90 degree. So is greater than xl region, the theta is over here, and the angle for xl is greater than region is positive from 0 to 90 degree, depend upon the xl and xc values, and this is xl is equal to xc point. Okay, now thank you. That is all for the moment, and in the next slide we will in the next lecture we will discuss this the selectivity and the numericals. Thank you.